All right, everyone, let's go ahead and get started. So please close your laptops and turn your attention up here. All right. So as usual, before we get started, technically, any questions about anything? Just so you guys know, we will be having the midterm, I think, as planned. I think we're going at a decent pace, so we don't need to push it back. And homework 2 is out, as hopefully all of you guys know. Please take a look at it. What do you guys think? Should I, like, every homework could give a little bit of extra credit if you guys get started on it early and, like, submit something? Yeah? People like that? All right. OK, we'll do that this time, too. Think of a proposal, please. Maybe by Wednesday or something? Right? OK. All right. We'll come up with a proposal and share it with you at the end of class today. OK?
Is it due next week?
It is due on this coming Sunday night, right? Yeah. So we're now going to be at about a week per homework assignment. All right. Any questions? Anything you guys want to talk about that related to the class or related to material we've covered before we get into it? Yeah.
I just want to clarify. The pumping lemma, it's some non.
Yeah. All right. Hey, everyone. Can we please focus? Yeah.
Some non-regular languages. Like, it doesn't say that every regular language, or it doesn't say that every non-regular language has to follow. Like,
right. No. First of all, the pumping lemma only applies to regular languages, right? So look at the homework. All right. So the homework will exactly talk about some of these issues. Yep. Excellent. All right. Anything else related to the midterm or anything like that? Any questions or issues on your minds? Yes.
Would you be able to give us some sample, like the midterms from previous semester?
We will. We'll release one sample midterm next week. Okay. And again, you know, as I've already warned you guys, right? The midterms, you'll see things on the midterm that you've never seen before, right? So the sample midterm is just a sample of the kind of things you've never seen before that might show up on the midterm, right? So just be ready for that. That's the whole point. That's why it's very important to come to lectures, because like, it's the way that we think, right? The way that we attack these questions. That is what I'll be testing you guys on. And again, really, the point is not really to test you. It's to have fun. I know this is always a little triggering, but I really mean it. Like, you know, I hope that you really just have fun with the midterm. That is, you know, you look at the problems and you're like, that's cool. I want to solve that. Yeah. All right. Yes?
One more question. I'm not sure if the homework 2 was released before the weekend, but if it didn't, would it be possible to have it released by Friday so we have, you know, like Saturdays and Sundays to work on it as well as the full week?
I see. Okay. So you're asking if we can. So we actually released it, I think, on Saturday night. Is that right? Yeah. Saturday night is when we released it. You're asking us to move it up one day and actually release it to Friday night.
I'm not sure if anyone has the same situation as I do, but I work and I go to school, so
right.
I have to, like, you know, Saturdays and Sundays are the only days that I actually can focus on studying, essentially.
Okay. All right. No. That sounds great. So we'll do that. So now there'll always be a little bit of an overlap between like when we release the homework and when the previous homework is due, but I assume that's not a problem for anyone. So we will do that. Thank you for asking. Yeah, we're happy to do that. In general, we're very happy to be responsive to you guys, right? We want you to have the best like learning experience possible. Okay. All right. if there are no other questions, then let's come back to the story so far, right? So we've been analyzing these DFAs and regular languages for a while. And it's been fun. You guys have figured out lots of interesting stuff about them. But as like reinforced in the last lecture, they are really limited, right? Regular languages are extremely limited. And kind of the prototypical problem, the one that we, in some sense, started with as a non-regular language, right, is like this L equals language, where we're looking at a string in 0, 1 star with an equal number of zeros and ones, right? From that, we extracted this like 0 to the n, 1 to the n language, but really it was just like the equal number of zeros and ones that was the driving factor from the very first lecture. That was one of the first things you guys suggested, right? So the fact that DFAs and NFAs, like the fact that they can't handle something as trivial looking as L equals just seems like very annoying, right? And like very problematic, right? That like the answer to this deep question of like, what can't computers do? They can't count forever, like that's just somehow a very unsatisfying answer, right? So today we want to move beyond that. So let's try to think of a way of coming up with a definition of a computer that is stronger than a DFA, right? And we already know that this is non-trivial, right? Because NFAs was something that we came up with that turned out to be just equal in power to DFAs, right? So like we know that not every strengthening will actually yield something stronger. And maybe one idea to keep in mind is like this language. We definitely want to come up with some kind of a notion of a computer that can handle this language. So let me open it up to you guys. Like, what do you think we should do? Like, what do we need to add to our notion of a computer so that it won't have these annoying problems, like the fact that it can't do L equals? Yeah. Yeah, right. So the most natural thing is that it's not that DFAs and NFAs don't have memory. It's just that their only memory is their state, right? The only memory they have is what state they're in, right? And of course, by definition, a finite state machine only has a finite number of states, and that's the problem we keep running into. So your idea is, why don't we add some sort of external memory, right? Some sort of unbounded external memory. Excellent idea, definitely worth a token, getting us started, right? So idea is to add external memory. And just to be clear, like we want to build up, right? Like generally speaking, when you're trying to build a theory, which that's what we're doing all together, right? Like we don't want to just start completely new unless we have to, right? So we're thinking now that we'll keep our machine, and here one thing where I'll put in a little bit of an input. Let's actually think of like an NFA as opposed to a DFA. Let's think about an actually like a non-deterministic machine as like our base machine, okay? And now we're going to add something to it, and some sort of memory. Okay, excellent idea. How should we do that? Like in what way should our machine have access to this memory, right? Because like, remember, our machine works by means of some kind of delta function, right? That used to go from like Q cross, remember there's like sigma epsilon that just like adds epsilon to it, to the power set of states, right? Because it can be in multiple states simultaneously. And by the way, also, starting today especially, I want you to think about non-determinism in like the multiverse way, where it's not that you're in multiple states simultaneously. It's like we make a new universe for every different like state that this machine could be in. Okay? So I want you to just think about it out for that. Yeah.
So
Uh-huh.
Everything that is stored in a separate DFA, right?
Everything that would be stored would be what? Sorry, what did you say?
DSA? Like a DSA of its own that's repeated like
Not sure I understood your question. So let me actually maybe I'm saying too many things. So actually let's just go back. So NFA. I'm just sort of throwing it up, putting it up there for right now. Let's not worry about that right now. Okay. So just imagine it's just an ordinary DFA for the moment. So it's just like standardly moving, but it just like has access to some memory, right? Does that already resolve your question, or does it not? That does resolve your question? Okay. Sorry? You're okay? Okay. Sounds good. Yes?
I have a question.
Mhm.
By external memory, do you mean limited memory or infinite memory?
Yeah. So like in order for it to be able to handle L equals,
Yeah.
it has to be some kind of unbounded memory.
Yeah.
Let me call it unbounded as opposed to infinite. So let me write that actually. Unbounded. And I'm just saying, I'm using the word unbounded instead of infinite just because infinite memory, like how do you make use of that? This is like not a physical thing, right? Whereas we can kind of imagine the idea of an unbounded memory as being, some ordinary memory. And whenever it fills up, you just go to the store and buy some more and add it to it, right? So like imagine you can just always go to the store and buy more memory whenever you feel like it, right? And the store always has memory in stock, right? Yeah.
So for the memory, would we able to use it in a way to just like store certain outputs from given inputs we give the DFA, and then we'll have like kind of like a cache where we just keep
Okay.
history of
Okay, good. Yeah, because that's exactly the question now, right? Which is like, if we're going to add memory, we have to change the delta function, right? The delta function somehow must get like access to the memory in some way, right? And so your idea is maybe think of it like a cache, like cache memory. Okay, so I assume what you mean by that is like there's a certain amount of memory that you can like access at any given time, and then you can like swap it for other parts of memory. Is that what you kind of mean?
well, if it's unbounded, then we can just keep adding. We don't have to swap.
Okay, good. So you don't have to. Okay, so if we did that, right, we definitely need to add some input here, right, to the delta function. And this is, I'm actually really glad that you asked that question, because I think this is going to make like put a fine point on it, right? If we just like stuck the entire memory here, right, then this is now an infinite like description complexity function, right? Like to write down this function delta would require an infinitely long table, because we don't know what the state of memory is, right? So that means like our computer itself would need an infinite description, which is just obviously not what we want, right? So that's essentially the problem that we need to now address, right? Is that we do not want this, right? I do not want like all of memory to be being accessed at once by the delta function, because we want to be able to write down the delta function, in some finite amount of space and say that's my computer, right? The computer still has to be finite. Make sense? Okay, definitely a great question, totally worth a token. Okay, ideas, is that right? Yeah?
We can look at the last thing added to the memory, sort of like a stack.
Okay, excellent. So another thought is we could think about the memory as a stack, right? I'll just write stack. And yeah, one advantage of your idea, which is definitely worth a token, is that then what we could think about as being given as input to the delta function, right, is basically just the top of the stack. Right? And that's perfect. It exactly solves the issue, because now we're only looking at one little spot in memory, right? So it's completely finite, and it makes sense, right? And so let's actually stick with this for a bit. Okay, definitely worth the token, sorry. I don't know if I already said that. So let's just think about how would we implement this, okay? So let's kind of just run with the stack idea and see how we might implement it. By the way, I'm sure you guys will come up with many other ideas, right? Like we don't have to go with the stack, but hey, he suggested it. The cache idea was a little more vague, right? The stack idea directly addressed this issue. So we're just going to run with this for a while, okay? Question?
I have more of a question about using a stack. So if
Mhm.
we're using a stack and we look at the top of the stack,
Yeah.
is the assumption that once we look at the top of the stack, we're done with whatever we looked at and that's kind of gone, or are we going to add it back to the stack somehow? If you wanted to look at that value again, that would be
Great. Okay, yeah, so I'm going to turn your question into a suggestion, right? So typically when you have a stack, what are the operations that you can do on a stack? Pop and push, right? So, so pop and push are the usual ways that we deal with stacks, right? So we would probably want to implement that. Like we would want our machine to be able to do that, right? So cool. Again, I'm just going to get us just started a little bit by saying that we had our input alphabet, sigma, right? So let me just say that the stack alphabet doesn't have to be the same as the input alphabet. So we will just define the stack alphabet to be gamma, okay? And as a general rule, it doesn't have to be this way, but we can think of that we can think of it that the input alphabet is just like a subset of the stack alphabet. It doesn't have to be. This is sort of just like a general suggestion. But like it could be bigger is the point I'm making, right? It's like it might be helpful for us to think of additional symbols as being available to us in the stack, okay? So like that will be like a new thing that will be part of the definition of our machine, right? Sorry? Yeah, clarification. Mhm.
Did you mean the stack alphabet should be a subset of all the available input alphabet, or the other way around?
I did write this correctly. I just meant that like when you are pushing and popping things onto your stack, it makes sense usually that you would want to be able to push and pop things from your input alphabet. But you might want to push something else also onto your input alphabet. So this is just a suggestion that like generally you would want to think about the stack alphabet as being at least your input alphabet, but maybe other things also that can just help you keep track of what's going on. It still has to be finite. So remember, everything that is, a part of the description of our computer has to be finite. Otherwise, it just doesn't make sense, right? Like this computer fits in this tiny little square. Even like the big computers fit in a room, right? So, or maybe a big room, but still fits on Earth, right? So like they're all finite. And we want whatever notions we're coming up with of computers to still be finite, right? Okay, cool. Yeah, so now we have the stack alphabet, right? And now we can think of the top of the stack as just being one element of gamma, right? Which is just whatever is at the top of the stack. So again, we'll think of this as top of the stack still. And again, if what I'm saying does not make sense, please ask a question. So far, all we're doing is like trying to implement the suggestion, right? Of like adding a stack to our machine, right? So we're like editing our NFA definition, right? The delta function in particular of the NFA definition, to add stack functionality to it, right? So what we've done so far is we've said we're in a state. We see some input symbol. Could be an epsilon transition. And we also just see whatever's on the top of the stack, right? Yeah.
We also need to include like an empty, like an epsilon, because we don't want to be.
Okay, sure. Why not? It's up to you guys. So if you want us to include epsilon, let's include it there, right? So like maybe for example, in the beginning when the stack is empty, then it just shows up as epsilon, right? Or maybe we don't care what's in the stack, and that is a way of using epsilon, right? So we can add it there. That's no problem. Okay, so like I think we have something under control when it comes to the inputs to our delta function, right? But we haven't yet like added like pops and pushes and things like that. So we need to think about that. How can we do that? What would it mean? And another way of thinking about it is, let me remind myself not to go, is that a reasonable place for you guys? Let me also just say that, you know, we want to think about things formally, but we also want to think about them in terms of like just drawings, right? So we still like have our initial state, Q naught, but now when we're doing a state transition, maybe we see our input 0. Maybe in the beginning we don't care what we see exactly on. Well, okay, sorry. Give me a second. All right. Let's say we see our input 0, right? But we haven't yet talked about the stack. And like when the machine is transitioning, it might want to do something to the stack, right? So what could we potentially do here that would just, you know, get things going? Yeah, in the back.
Push 0 onto the stack.
Sorry?
We could push 0.
Yeah, so like one thing we could do is just like add an instruction that says push 0, right? And just to be clear, what does this mean, right? This means that we actually, like when we do this, let me just write it here. So when we have a transition like this, and thank you, that's definitely worth a token. When we have a transition like this, then the machine like doesn't like, you know, bother to look at the top of the stack. What it does is it just pushes a 0 onto the stack, right? So and that's okay because there's like one individual instruction, right? Maybe just before that it looked at the stack, so that's okay, right? So when we say push 0, then we're just, you know, we have the stack at the beginning. Maybe it's empty, and then at the stack after this, we'll just have a 0 on it, a 0 in it, right? Question or comment or suggestion? Yeah. Sorry? Yeah.
This actually feels pretty interesting that, like, now I can imagine if you just told the machine, like, when you do this, you have to be popping a certain thing, like, we could interpret that under, like, multiple worlds idea of, like, oh, like, they can't do that thing based on what's on the stack, they just won't do it. I'm talking about, like, popping.
Excellent. Okay, great. So maybe I'll just run with you as like the second idea, right? So obviously we want to do pops. So let's draw that. And again, maybe what we do is we see a 0 on the input, and then we decide, actually, maybe we'll think of this as coming out of that guy, right? And then we pop a 0. And what this will do is, again, it'll check the input, make sure there's a 0 on the input, right? And if there is a 0, then it'll pop the 0 off the stack, right? But then related to what you were saying, suppose there was another instruction that said 1 pop 1, right? Then even if the input string was 0, 1, it still can't do this, right? Because there isn't a 1 on the top of the stack to pop. Does that make sense? And that's exactly the point that you were making, right? So first of all, definitely worth the token. And I want to make sure this makes sense, right? Like just the way we're doing it. And it's very NFA-like. That's actually why I was saying we want to think about this like NFA-like. Question or comment?
Means that for like any input, you not just are mapped to some other input, but you're also mapped to something that could have taken off the stack. So I would think that delta should be the power set of like Q cross gamma epsilon.
Yeah, excellent. Good. All right, so you're suggesting let's implement it. But actually, sorry, before I take your suggestion, I want to make sure there are no questions. So just, does that make sense? Like it's just basically it's an NFA that can mess with the stack, right? It has the option of pop pushing and it has the option of, sorry, it can like take a command that pushes. Now a command that pushes is always available, right? Because like I can always push something to the stack. There's nothing that can prevent me from that. But when I'm popping, I can only do that if the thing that we want to pop is actually there on the top of the stack, right? So pop 0, what this really means, and I'll just maybe write it that way, maybe in another color, right? This really means like a code block. If top of stack equals 0, then pop, right? So like that's actually what, when we write pop 0, it's actually implementing this code block.
I don't think you need it because you are already given the top of the stack, right?
Mm-hmm.
So you know what's on the top of the stack. And usually in stack operation, we don't specify what's the algorithm we pop. We only specify when we want to pop. And you always pop the top of the stack, right?
Yeah, exactly. So I'm just saying that this instruction, when I draw it, we interpret it as this instruction. That
Oh,
if the top of the stack is 0, then pop. Otherwise, don't do anything,
okay, so
right?
that's
Or otherwise, don't take the transition.
so that's part of your delta, right? It's not your output. It's more of like an instruction your delta.
Absolutely. Yeah, and we haven't done that yet, but he was about to suggest a way to do it. I just want to make sure that everyone was clear on it first, just like what we're doing, right? Do you want to now suggest your idea? So you're going to, let me use the black marker. So you wanted to make this Q cross gamma, right? Because, yeah, we might want to be pushing something onto it. So this would, again, be like gamma epsilon, because we could also not want to be pushing something onto it, right? And then finally, we also just need to specify what we're doing, okay? So this is something which I'm not going to keep asking because sometimes people forget that you can do this. So literally, we just have like pop and push, right? So this is just saying that when I'm taking a transition, I can specify either pop or push, right? If I'm specifying push, then whatever I put here is a thing that I'm pushing. If I specify pop, then whatever I put here is a thing that I'm popping, right? And that's definitely worth a token. And question?
Are you not allowed to have no ops then?
Yeah, good. So if you guys want, we can add. So yeah, maybe I'll write it this way. That let's think of it as something optional. Like this would be like 0, comma, no op. Okay? But observe that this, sorry?
You can just push epsilon or pop epsilon, right?
Right. So, and yeah, this could be encoded as like push epsilon, right? Or like this is equivalent to pop epsilon, right? But I also want to point out that we don't actually need it, right? So could anyone see, suppose this was not allowed. Suppose that I just did not allow that to happen. And I wanted to implement the no-op. How could I do that? Yeah. Yeah, right? I could just 0, comma, push some funny symbol, and then epsilon, comma, pop, funny symbol, right? Just with a new intermediate state. So if this was Q, and this was S, I just have Q and S here, and just some new state Q prime, right, in the middle. So these are exactly interchangeable, right? So observe that we don't actually need a no-op, right? So in class, actually, I will want you guys to not imagine that no-op is not allowed, right? So you actually always have to push or pop something, okay? Let's just say that's the rule in our lectures, and it'll just be to make things slightly easier as we proceed. And anyway, we can implement it, right? And thank you, that's definitely worth a token. Cool. So does that make sense? Does that make sense so far? Maybe one other thing I want to emphasize one more time is that this new notion, this like stack machine that we have defined, just because I'm suggesting it, I don't know, you guys did not suggest this. Let's just think of it as being non-deterministic. So we can actually have multiple options coming out of a single state. And if 2 of them are possible, then we just spawn a new universe. And in one universe, we have the stack evolving in the way of one of the instructions, and in the other one, we have the stack evolving in the other way. So observe that there really could be 2 different universes with 2 different stacks at any given moment, right? Or in fact, many different universes with many different stacks, right? Another little observation is that as soon as we've added this, well, okay, kind of, again, similar to NFAs, these kind of stack machines can go into like infinite loops, right? You could imagine that there's some state, and it just has a self loop on like epsilon push 0, right? And it's just going to keep pushing zeros to the stack, right? And it'll like never terminate. In that case, we just say it doesn't accept, right? Because it's not accepting. Our machines only accept when they reach an accepting state after they've consumed the input. So that rule is still the same as it was before. Question? Right. So good. So actually, let me just say again that in class, we are not going to have epsilon allowed. Okay? So in fact, I don't know if I wrote that somewhere else. Yeah, no, I crossed it out. Good, right? So in lectures, the way we're going to look at these machines, you actually have to always pop some actual symbol or push some actual symbol. Okay? Now, I will tell you guys that in the book, like we're moving on to the next chapter right now, and like in the book, they do allow it. They don't define it quite this way, but all these definitions are equivalent. I think this one is a little more natural, so we're going to run with this one in the class. Okay? Yes?
For our homeworks and anything like that, are we allowed to use it, or is that also off limits?
No. In your homework, whatever we ask about these stack machines, right? You can use either the definition in the book or the definition from class.
So I
Either one is fine. Yeah. Whatever is more convenient for you. Okay?
Is that only for in-class discussion, or also for the
Again, for any homeworks or exams, you can use either one, whatever you just make it clear that I'm using the definition from class or I'm using the definition from the book. Okay? They're anyway equivalent, so there's no difference between them. It's just like via this simple transformation, right? Do you have a question? Yeah.
Yeah, for the infinite loop suggestion, how would you be able to tell if you're just halfway through the input or if you're never going to reach it?
Right. So what I meant was just that, like, suppose this was the entire machine, right? So like, this machine is just never going to accept anything, right?
Yeah.
Because there just isn't any. First of all, there isn't even an accepting state, right? The only way in which I still felt like it was worth pointing it out is that our stack machines like do things, right? So like this machine seems like it would just keep pushing 0, right? It'd be like, all right, the only option I have is I can push 0, no matter what the input is. Okay, I'm gonna keep pushing 0, right? So it like keeps pushing 0, 0, 0, 0, 0. But despite that, it just never terminates, right? It never bothers to accept. So even though it seems like it's some very hardworking machine, we're just gonna say it just rejects. Like for us, we just say it rejects.
Okay.
That's all I was saying. Does that make sense? Yeah.
Even if there's like inside a bigger machine, there's some state like that's doing something like that, and it's kind of infinitely doing that forever. It would just.
Good, good. Okay, yeah, maybe I'll write another example. So what if we had something like this, right? And this was accepting. Okay? So there are many, like infinitely many universes being created, right? But this machine would still accept the string 0, right? In fact, if this is a machine M, the language of this machine is exactly 0, right? Because the only universe that matters is the one in which we only pushed a single 0 and then popped it and accepted, right? But there are other universes in which, you push 2 zeros and then you popped one of the zeros and then you accepted. That's fine too, that also accepts. So that's also okay. But yeah, that's sort of what's going on. That makes sense? Okay. I saw there was another question hand. Maybe it already got answered. Yes?
I have a question.
Mm-hmm.
Are you allowed to check whether the stack is empty or not, or are you just allowed to check the top of the stack?
Good. Yeah. So what you're asking is whether you're allowed to check whether the stack is empty. And the way that we've defined things so far, we don't allow that, right? Which seems kind of annoying because checking whether the stack is empty seems like a good thing to be able to do, right? So I'm again just going to show us how we can, let me just start erasing stuff. So actually, what am I doing? Why am I showing you stuff? All right, she asks a great question, all right? Definitely worth a token, which is, wait a second, how can our machine check if the stack is empty, right? We don't have any way of doing that built into our description of the machine. So what should we do? How should we check if the stack is empty? And yeah, let me ask you to.
Yeah, so let's say the accepting state also requires the stack to be empty. Then maybe you could do something like we push a limiter that signifies that.
Excellent, right? So the idea is take your starting state and in the beginning always push a funny symbol. Let's call it like $, okay? So we have a special funny symbol, which is our bottom of the stack symbol, right? And then you have whatever you want, stuff happening in your machine, right? And then when you wanted to accept, instead of accepting right away, what you do is we don't care about the input, and we just pop the funny symbol, and that is the way that you accept, right? This guarantees that when you actually accept, your stack must be empty, right? So this is a way of basically checking whether your stack is empty and only accepting if your stack is empty, right? So yeah, this is a great question, definitely worth it. And solution's also definitely worth a token, thank you. And as a general rule, I will advise you to do this. Whenever you're building a stack machine, you don't have to make sure the stack is empty when you accept. Like that example is one that doesn't do that. But it just makes reasoning about these machines so much easier if you like maintain that as a rule of thumb, that any machine you make will only accept if the stack is empty. This is a standard way of just doing it. Like make all your machines like this. And furthermore, if we wanted to just empty out our stack, we can anyway have like epsilon pop a for all a in gamma, right? I could just add a self loop that lets you pop everything off the stack. And then, sorry, gamma minus $, right? We don't want to pop the $. And then the only way you accept is by popping that final $, that gets you to the accepting state, right? So kind of without loss of generality, we can implement a tester for the bottom of the stack by doing this. And again, I just really advise you guys to do that, okay? Everything else about our machine is the same. The only thing we really change is the delta function, and we've added this stack alphabet, right? And okay, maybe as opposed to how we did things, last time, let me just give you the name that the book uses. So these stack machines are called PDAs. Okay, so again, it's going to have Q naught, sigma, gamma, and then this delta that we defined, right? Wait, I'm missing something. Let me just see. Oh yeah, final states. And of course, our accepting states, right? Everything else is the same. The only thing that changed was delta in this way. And of course, we added our alphabet. Yes? Yeah, so it's actually not, right? Like the only thing that, remember how when we define things, we would always have kind of like two definitions, right? The first is like the data structure that just holds the description of the machine. This is like the data structure that holds the description of the machine. All these things are finite, so this is a finite description, right? Then we would have another definition that would say, okay, how does the machine actually work? So in that definition, which we won't write down right now, but you guys can take a look at it in the book if you'd like, we would just do the stack. Like whenever it takes a transition, it modifies the stack according to either the push or the pop, and it only accepts when it reaches an accepting state, right? And again, it does that like, and if there's more than one option, then it creates an additional universe, and it evolves the stack differently in the two different universes. Yes? Right. PDA stands for Pushdown Automata. I don't know why it's called that. It's just a historical name. Okay. Cool. So now we have at our disposal an unbounded memory that comes to us in the form of a stack, as you guys suggested, right? And this gives us a lot more power, right? We can count forever now, right, by using the stack. So let's actually take up sort of the challenge of solving our L equals language. So while I erase, please think, how should we do that? How can we build a stack machine, a PDA, that can actually decide the L equals language? How should that work? And that will be sort of the main thing that we do for a while right now. Okay, and sorry, I will just get us started because I want to maintain this invariant. So let's just say that the first thing we do is epsilon push $. Okay, so that's just how we get started, just because I want us to always do that. Okay, so we have our bottom of the stack symbol placed there. Okay. And now, yeah, let me ask you. Okay, great. So what you're saying is we could have like a self loop. Is that right? And if I see a 0, then I push, let's just say a 0 onto the stack. Does that work? And then if I see a 1, I can pop the 0, right? Like I'm counting it against the 0 that I pushed onto the stack, right? And just to be clear, again, just like following that rule, let's just, I'll just draw it downward. So I can also have an epsilon pop $. That gets us to our actual accepting state, right? Awesome, definitely worth a token. What do you guys think? Does that work? If it doesn't work, can you raise your hand and suggest to me something on which it doesn't? We're definitely worth a token, though. Did you? Sorry. Yeah, in the back.
The input is 0, 1, 1, 1.
Okay. Hold on. Wait a second. Your input has to be, or did you want to give me a string that's not in the language on purpose?
Yeah, like 0, 1, 1 as an example. Like you want to see if it has the same.
Well, if we see a 0, 1, 1, we should not accept, right? But in fact, we will not accept. I'm still glad that you asked the question, right? So let's think what'll happen if our input was 0, 1, 1. So we would push, so like after, right here at this stage, the stack would have a $sign and a 0. You agree? Yep. Right? After seeing the 1, it would have been popped off, right? So it would look like that, right? But then the input is not finished yet, so we cannot take this, right? I mean, we can take it, but then we're going to die right away, right? Because there's still some input left, just like with NFAs, right? And the stack is empty, so we can't pop a 0. So this machine just dies, right? And we reject, which is what we should do, right? So this indeed does reject, and that is good. So that is not an example of an input on which it doesn't work, but it was still a great way to get started. So it's still totally worth a token, okay? And let me try to call on someone who hasn't raised their hand recently. You? Okay, sorry. So you're saying 0, 1, 1, 0, right? So that should accept, right? And in fact, let me just make it even simpler. Still taking your idea. What if it was just 1, 0, right? If the input is 1, 0, we are in trouble, right? Because there is no 0 on the stack for us to pop, so we can't take this transition. There's obviously not a 0 on the input. We can't do that. This anyway will die right away. So we just die right at the beginning, right? So in fact, this rejects, which is bad. All right, so thank you, definitely worth a token. Do you have an idea for how we might fix that?
We have like 1 push 1.
Yeah, excellent. So let's just add 1 push 1, right? And actually that's confusing. Let me try to make myself some room. And then 0 pop 1, right? So now there are multiple options that we can take. That's what you suggested, right? Yeah. Awesome. Excellent. And now we're great. We won't reject this anymore, right? At this point, we would get here. Our only option would be to push the 1. So we could end up in between with a stack that looks like that, right? And then at this point, we would just pop the 1 and accept, right? So this accepts. Excellent. All right. Awesome. Again, definitely worth a token. What do you guys think? Does this work now? Will this be able to handle any input? Any thoughts? You don't have to give me a proof, but I do want to get an idea. Like, what are you guys thinking? Yes? No? How many of you think this is done? Like, this is definitely going to work for every single input? Okay, I see a smattering of hands. How many of you think it's not done? Like, there's something wrong with this. You're not sure what, but something is wrong here. Okay, I see a few, like, sneaking suspicions. All right, so any of you who have a negative opinion, who think it might not work, would you like to share why you think it might not work? Yeah.
Is there any chance we've run into an issue with the fact that we always have to read off the top of the stack, and so you might end up with some string where it almost makes me feel like there's something kind of palindromic about it, if that makes sense. Like every time you put a 1, or and you push a 1 to the stack, then you have to pop a 1, which means you have to put a 0. So maybe you can't get the ordering you want.
Okay, all right. Basically what I'm hearing from you is like, what if there is some funny order and you won't quite have the option you want, right? Very reasonable idea or worry, right? Totally worth a token, thank you. Any one of you want to propose a concrete input on which you're worried it might not work? So just to be clear, I want an example of something that is in the language, right? L equals, but we don't necessarily think this machine will accept it, right? I do want to make one observation, which I hope you guys all agree with. By the very nature of this machine, if this machine accepts a string, it definitely has an equal number of zeros and ones, right? Because the only way it can ever accept is if the stack is empty. The only way the stack can ever be empty is I saw an equal number of zeros and ones, right? Because like, if I pushed a 1, the only way to pop it is to see a 0, which will exactly cancel out. If I pushed a 0, that means I saw a 0. The only way to pop it is to see a 1, which will exactly cancel out, right? So clearly, if this machine accepts the string has an equal number of zeros and ones, the question is there some string that has an equal number of zeros and ones which this machine doesn't figure out a way to accept, right? So that's what I would like from you guys, is like an example of something that you think that has an equal number of zeros and ones, and you think this machine might not be able to accept it. Yeah, in the corner there.
What if it started with a lot of zeros?
Okay. Wait, so just something like that?
But like more zeros at the start than
remember that the stack is an unbounded memory, right? The stack, you can keep pushing things onto the stack forever. Like that's the whole idea. Like that's why we added the stack, right? The stack is unbounded memory. You can push as much stuff onto it as you want, right?
So why is that different than being able to make as many states as you want?
So the way that I would describe it is that there are runtime properties, and then there are like static properties of a computer program, right? When you have a finite number of states, then our computer program, like our computer, is described by just these sets. All these sets are finite. That means that the program itself is finite. Do you agree? So that's what we want, right? Now, at runtime, the amount of memory that our machine wants can keep growing unboundedly, right? And we like imagine that like what happens is like, let's say we're running the program and it says, hey, I'm out of memory. Then you just go run to the store, buy some more memory, stick it onto your computer, and then it keeps running. And it's, oh, I ran out of memory. Then you go to the store, buy some more memory, stick it on, and like imagine the store never runs out, right? Then that's our model of computation right now. Is that cool? All right. So at least this will not be a problem, right? Like we actually literally can have any number of zeros followed by any number of ones. So this is not a counterexample. Yeah?
I kind of want to say when, like, what happens if we like run empty string, but then we have the dollar sign.
Yeah, empty is fine, right? Like because empty is you just push the dollar sign, you go straight to popping it, and you already accepted, right? So that is fine. It's not a problem for us, right? Okay, you guys are okay. So one thing I'm hearing is that you're having trouble, although I see some like hands partially in the air. Yes.
I just had a question.
Okay.
You said earlier that 1, 0 accepts. How do you know when you hit the 0 whether or not to push a 0 or pop a 1?
Exactly, right? So this is a non-deterministic machine.
Yeah, but does that mean like there's like each stack is like unique to like the state it's in?
Each stack is unique to the universe that it is in, right? But okay, I really like what you're saying. So let me actually just devise an input that addresses your question, okay? Because this doesn't quite. Well, okay, no, yeah, it does. Okay, good. All right, sorry. I will just think about the one that you're talking about, right? So what you're saying is after we see this 0, right, there are actually two different universes we could be in, right? There's option 1 and option 2. In option 1, we have just popped the 1, right? And like this is the good one. But in option 2, we have the dollar sign, we have the 1 that we already had, and we actually just pushed another 0, right? Both of these universes exist, right? This one will go on and accept. And remember, just like in an NFA, if even one universe accepts, we accept. This one is just stuck, right? At this point, it can't do anything. And it's run out of input. Since it's run out of input and it can't do anything, it's not in an accepting state. It's just in this state, right? So this universe rejects. But this universe accepts. And as long as one universe accepts, we accept. That's just the way NFAs work, and therefore the way that PDAs work. Yeah.
We said that like before NFA, we said that each state is like actually a set of states. Does that mean like each state is a set of states that have its own stack?
Yeah, so actually that interpretation no longer works, right? We're not just in a set of states anymore. We really have to think about it in this like multiverse interpretation. Only the multiverse interpretation makes sense here. Okay, cool. Yes?
One of the things that we maybe didn't really address was like the switch between having more zeros and then more ones. Like in terms of like initially we would say like we pop a bunch of zeros and then our stack would be mostly zeros. And then we'd like have this tug of war between like
Okay. So I hear some ideas, but let me just say one thing. And again, if you have a question, please do raise your hand with a question first. But I would really like us all to just think of some specific inputs. It's okay if it works, right? If it's okay, like just give me some inputs. Let's think about them. Let's actually let's like try to work our way through a few example inputs and see what happens. Yeah.
I want to say, first of all, I think the machine works because you
Okay.
have proved that in the second half of any
Okay.
input.
All right. I'm gonna pause you for just a second. We have one vote, at least, for it works. So she's actually just convinced right now, right? That's great. Some people are not yet convinced, right? So for the people who are not yet convinced, give me an input. Let's take a look at an input and let's see how we can make it work. Yeah. Do you want to give me an input?
Yeah, 3, 1, 6, or I guess like 6 or like.
Sure. I guess this is 4. Okay. How about that? Okay. Cool. All right. So great, thank you. Worth a token. All I wanted was an input. You gave me an input, right? You tell me how are we going to work on this.
Push, pop, pop, pop.
Excellent. Yeah. So let me actually kind of draw it this way. Okay. So what she's saying is that we see these ones and we just keep pushing. So think about like this is like the stack, right? And it just has a bunch of ones on it. Sorry, let's say a dollar sign is at the very bottom, okay? Okay. Then we see the zeros, and then you want to just pop, 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 right? Actually, I should have drawn it after the ones. Okay. Sorry. Actually, how about this? I'm going to draw one of the ones on the line. Okay. And then this one got popped. This one got popped, and then finally it went all the way down to 0, right? And now you want to start pushing again. Is that right? Yeah. Right? And then we start popping again. And then we accept, right? At that point, we've accepted, right? So this is one possible way that our machine could evolve, right? This is one universe, has this like diagram, this like stack diagram, right? And hey, we got to an empty stack, which means we accepted at the end, right? So it works. And thank you, that's definitely worth a token. All right, so far she's winning. Yes?
I have a question. Could we design the PDA in a way that for every push, we do one pop right after that? So, for example, in the case of this input, we pushed 3 times and then we popped 3 times. We pushed 2 times and then we popped 2 times.
Yes.
What if we did a push, pop, so on and so forth, all the way till the end of the input? That way, we don't have to count how many pushes we did, so we could do the same amount of pops. And that way, if we have anything left over, essentially we either have a 0 or a 1 in our stack right after the special cases.
So I really like your suggestion, okay? Because it's something we should all think about, right? So what he's saying is like, could we somehow design a PDA in a special way so that it always does push pop, push pop, push pop, push pop, okay? And it would, and I'm seeing some no's here, right? And in fact, not only is the answer no, but if you had a machine that always did push pop, push pop, push pop, it's no more powerful than just a NFA, right? And the reason is you're not using your memory, right? You could just add to your states like whatever you pushed and whatever you popped, right? So in fact, it is absolutely critical that we use our memory by pushing for a long time and then popping afterwards. It's the only way we have any hope of solving a non-regular language like L equals, right? But it was a great question. Still worth a token. Great, good for us to think about that, right? So it's absolutely critical that whatever machines we build, they have the capacity to build really long stacks, right? Yes. You have an input. All right, let's do it. Actually, sorry. 1 second. All right. I don't know how long your input is, but let's. Okay, good. What is it?
I was just thinking, just take any reasonable and add like a dollar sign in the middle.
Well, remember the input is only zeros and ones, right? Input doesn't have dollar signs. Right? Yeah. Does that ruin your example?
Yeah.
Okay. That's all right. That's okay. Okay. Any other inputs anyone want to suggest? This is like free tokens. Come on, guys. Like, just give me an input. You know? Yeah. Oh, sorry. Yes.
0, 0, 1, 0, 0.
0, 0, 1, 0, 0. Okay. That is an input, but it's a rejected input, right? I need you to give me an input that has an equal number of zeros and ones. Yeah. Sure. Okay. All right. Okay, cool. Right? Awesome. All right. You get your token. What do you guys think? Is our machine going to be able to handle this? Let me ask someone who is not her. How would you handle it? Yeah. Okay. So push, pop, push, pop. Right? Yep, that works. Right? This is 0, 0, 0. It has a 0 here. Sorry, that should have been, anyway, okay. 0, and then 0, 0, 0, 0, 0. And then, yeah, you just pop. Right? And that'll work, right? Okay, thank you. Definitely worth a token. Question?
Is there a way to determine like how many possible universes there would be for a particular input?
Yeah, no. You know what? The answer is no, because of those annoying infinite loops, right?
Okay.
Because there are these annoying infinite loops, you just don't know. Thank you so much. Right? There could really be an infinite number of universes for any input, if the machine has like an infinite loop somewhere.
Right. So, but to reason about like which stack is like the one that will lead to the right answer.
Yeah.
It requires some amount of intelligence.
It does, right? So this is a great observation, right? Is that what we're drawing here is one of the universes, right? But there are many universes. So the question is, like, which universe, or let's call it like a run, right? Which run of the machine is the right one? Right? It's a great question. Definitely worth a token. You know, like this is the thing we have to think about. So, okay, I hope that by just running a few of these examples, you guys are all getting convinced that she was right? That this actually does work. But how do we prove that? Right? Like with all of our DFAs and NFAs that we constructed, in some sense, when you constructed it, there was a pretty simple, like intuitive explanation. Well, sometimes not that simple, but still reasonably intuitive explanation, even on the homeworks, right? As to like why does it work? In this case, how do we know? Right? It's actually fairly non-trivial. It's not so clear. As soon as we've added this like unbounded memory, it becomes a lot trickier. So let me hear some thoughts. Yeah.
My idea is that, like, aiming
So sorry, just say the last part again.
We can argue that you can give us any input that isn't language, and then we can choose, like, we can pick the right path through on determinism.
Sure. But the question is, as the provers of the theorem, which path should we pick? Like in the proof.
Oh, I think we just want this back to be like the same color, or like uniform, like either all ones or all zeros.
Okay, but in this example, right, the stack was not always all ones or all zeros. It was initially all ones and then it became all zeros.
Yeah, I mean, like, at any given.
At any given moment. Okay, I love it. Okay. So, what's your name?
Tom.
Tom? All right. So let's call it Tom's run. Okay. So Tom's run is the one where at any given moment the stack is like monochromatic, right? It either is all ones or all zeros. So stack is always all ones or all zeros at any point in time. Okay. First of all, is Tom's run unique? Is there only one universe that corresponds to Tom's run? Can we? Sorry. You're here. I'm hearing some yeses. Can someone raise their hand and give me some kind of explanation as to why that might be true? Yeah.
I think yes, because every time we push an input, the next input is absorbed or like consumed in order to pop the previous one. So like if it's all zeros, then if there is a one.
Good. Yeah. Let's take that what you're saying slowly, right? Suppose so far the stack only had zeros in it, okay? And then let's just say that we saw a 1, right? So we only have two options, right? These are the only two options when you see a 1. We can either push a 1. Well, we can't do that. Tom's run does not allow us to do that because we have zeros. So now we only have one option. We can only pop, right? Similarly, if we see a 0, well, I could pop a 1, but that anyway is not even possible. I have zeros on my stack. So that's not even not allowed. So the only thing I can do is push a 0, which agrees with Tom's run, right? And similarly for 1. So absolutely, right? You're exactly correct. Tom's run only exists in one universe, right? There's only one universe throughout the whole evolution of this machine that is part of Tom's run, right? Which is awesome. Thank you, definitely worth a token, right? So, so Tom's run is indeed unique to one universe, which is great, right? And now the claim, right, that's implicit in Tom's run and Tom's suggestion is that Tom's run will always get the right answer. Whatever the input is, Tom's run will accept it if and only if there are an equal number of zeros and ones. Right? Okay. So that's the claim. How should we prove it? Yes?
Suppose for the sake of completion that we don't take the right path, and then we don't have either all zeros or all ones, and then we try to push in.
Well, okay, hold on. Maybe I didn't want to go as like formal as like writing down a proof, but maybe it's helpful. So let me actually write a little bit more. Write a little more down. So we have a claim toms run always kind of gives the right answer. Okay. And now we want to prove this. And remember, we already observed, so let me just write it as like trivial. If our machine accepts this implies x is in L equals, right? That's just like by construction. We don't even need Tom's run for that, right? So the only thing we need to prove is the reverse. So now we say suppose x is in L equals, right? And now we want to prove that, so now I'll just write it this way, want Tom's run accepts x, right? That's what we want to prove, okay? So with that like background, we can start to think about how the proof might proceed for this like subclaim, right? That Tom's run accepts x, assuming that x is in L equals. And yeah, okay, I see some hands in the air. Let me go to you guys. Yeah.
I wanted to say, if we want to prove it, would it be simpler to use reduction in this case to prove that Tom's run accepts x?
Yeah. It turns out that it will be, but it'll be a little complicated. So let me actually just say that instead of continuing with the proof, we'll sort of move back to intuition, okay? Because we're not quite ready yet, is actually my feeling from what I'm hearing from you guys. Like, we're not quite ready to actually give the proof of this, so we need to still build some more intuition for it. Yeah. So maybe it's useful to take a look at these two stack diagrams, right? And like, sorry, this stack diagram should have started right there. Let me draw that more correctly. And then think about ideas, right? Like just some intuition. Why would it be the case that if the input has an equal number of zeros and ones, that Tom's run will in fact give us the right answer, right? And all right, I definitely see some hands there. Yes, you've been asked. Yes.
I think we can make an argument on the size of the stack given any x. Because
Okay.
if you're given an x, it must be finite, right?
X is
So the
finite.
length of x can be set to n.
Okay.
And n must be even because we know that like
Equal
n
number of zeros and
yeah.
ones, yes.
And since you know your stack is monotonic, you know
What do you mean the stack is monotonic?
monochromatic. The word you
Monochromatic.
yeah, the word you used, whatever word you used to describe all zero or all one.
Okay.
At any time, it can only be all zeros or all ones.
Mhm.
So your size of the stack will only be maximum of the two possible like 0 or 1 situations, and all of them will start decreasing from n over 2, right? And at each turn, like at least at the second half of your string, as you go like closer to the end of the string, it's going to be like smaller equal to n over 2 minus 1 over 2 minus 2 until 0. And you can prove that your stack goes to empty.
Okay. I'm not sure exactly how to interpret what you said. I definitely want us to go a little bit slower, though.
Okay.
Okay? I guess here's a first question, okay? Our machine only accepts when the stack is empty, right? So the first thing we need to prove is that Tom's, like the thing that we're trying to prove is that Tom's run does actually go all the way to empty at the end, right? So, okay, all right. Let me just put that up as like ideas. Sorry. Oh, I shouldn't raise that. All right, sorry. Okay, yeah, that's our actual machine. Let me I'll erase the definition of this. Okay, so I will just put up this idea. Oops. Pairing up zeros and ones, right? That was one of the thoughts that you had, that if we can pair up zeros and ones, where one got pushed and one got popped, right, then that would help us proceed. And that's certainly true, okay? I'll give you a token for that, right? But like, we do need some way of thinking about like any input that has an equal number of zeros and ones, and like making an association between that and like what would Tom's run actually do on it, right? So I want you to think about that a little bit. Yes?
Like the state of the stack at any point in time kind of encodes like the difference between the number of ones and zeros.
Ah, beautiful, 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 beautiful observation. Okay? So let's think of the y-axis as the number of zeros minus the number of ones, right? That was her idea, right? That like, let's take a look at the difference between the number of zeros and the number of ones, right? And let the x-axis be the input, as usual, right? We, of course, start exactly at 0, right? And we know that we end exactly at 0, right? Because there are an equal number of zeros and ones in the original string, right? Now, this diagram has exactly 45-degree angles at all times, right? It can go up and down, and let's write it that way. Right? This could be kind of like a general view, right, of some input. And over here, we have more zeros, right? And down here, we have more ones, right? So what is your claim about, like, what would Tom's run stack diagram look like on this?
So anything like that's positive, like in the zero zone, would be a stack that's completely zeros.
Mm-hmm.
Anything in the one zone is a stack that's all ones.
Yeah, right? So basically, anytime you're up here, the stack has all zeros. Anytime you're below, just reflect it and make it all ones, right? So that is a very nice claim. Right? And this is actually a really beautiful idea, right? Totally worth the token, right? That if we just think about it from this perspective of the number of zeros minus the number of ones, we actually have like a really intuitive idea, right, of like what should happen in Tom's run, right? Because whenever we have more zeros, that means we have like zeros to give on the stack, right? Because as soon as we saw the first 0, we started pushing zeros, right? And any number of 1s we see here, we have zeros to give, right? We have zeros on the stack that we can just pop off whenever we see a 1, right until we cross the x-axis again, right? And when we cross the x-axis, that's when we have to start pushing 1s. And we know below here, whenever we see a 0, we have a 1 to give, right? We have a 1 that we can pop off and keep going up, right? So this diagram basically is a proof, right? Like the cool thing about stack machines, these PDAs, is that unfortunately we do have to prove, like we have to come up with a proof in some sense of like why does it work properly. But when we look at this stack diagram, and when we have some like nice way, if we have a nice way of looking at the input and thinking about it in terms of like some quantity that relates to the stack, then a nice diagram like this basically just is a proof, right? This just shows that it is going to work, right? Just based on what I said in words, right? That like whenever we're above the x-axis, that means we have zeros to give on the stack. Whenever we're below the x-axis, that means we have 1s to give on the stack, right? Sorry, any questions about that? Yeah. Mm-hmm. Okay, so let me actually let me take everything you said and just take one word out of it. Okay, so induction, right? It makes sense. That's kind of related to what you were saying earlier. That if we actually wanted to prove this formally, we would probably do it by induction, right? Based on like the length of the input. How would we do it is not as easy, right? So let me. Okay, so if we're inducting on the length of the string, of course the base case is totally trivial, right? Like empty string, yeah, we accept, no worries, right? But the inductive step, we want to argue that we've already proven everything for smaller strings than n. And we want to somehow take our current string of length n and reduce it to some smaller strings, right? So I would like you guys to look at this nice diagram and think of what are some ways. Okay, one way will not be enough. Let me just tell you. Okay, what are some ways of taking a longer string and decomposing it into smaller string or smaller strings in such a way that we can apply some sort of induction hypothesis? And let me go right behind you. Yeah.
I don't know if this is like that useful for the proof, but if you like argue that every time your stack reaches 0, you know that substring under n.
Perfect. Yeah. No, that's a beautiful idea, right? So what she's observing is that there's one type of inductive step that's really easy, right? Which is whenever we cross the x-axis in this diagram, we have now constructed strings that have an equal number of zeros and ones, right? The left string and the right string, right? And each of them have a smaller length, so by induction, our machine would have accepted the left string and accepted the right string. And again, by construction, our machine only ever accepts with an empty string, an empty stack, only ever accepts with an empty stack. So we know that at this point, the stack would have been empty, and then it could just continue on, right? So whenever we cross the x-axis, that is one way that we can apply an induction and get smaller strings and proceed, right? So totally worth a token, right? So what that also means is that we only really have one case left, which is we're entirely above the x-axis or entirely below the x-axis, right? Everything else is taken care of by this. So let me, actually I'm just going to erase the example now. Okay. And let me now just kind of draw the stack picture of it. And again, just without loss of generality, we know we're going to have two cases, right? The 0 case and the 1 case. Let's just do the 0 case, right? So we know that the stack starts with zeros, and whatever it does, it never crosses the x, like it never goes all the way down to an empty stack and then starts again, because that's already taken care of by her observation, right? So we only have this case. We know we saw a 0 in the very beginning, and which means we must have seen a 0 in the input. And that 0 did get popped off at the end, right? Because that's the only way we can finally end up with something that has an equal number of zeros and ones, right? So what's the induction here? Yeah.
Could you just like sort the input? Because if they have the same number of zeros and ones, rearranging them will still have the same zeros and ones. And so you can turn a kind of gross jagged graph like that, just like a single pyramid. And you can just perform induction on that middle point where you just group the 0 and the 1 and get rid of it. You just keep doing that.
But we want to prove that it works for the original input, not the sorted input, right?
But they would prove if and only if for each other, right?
Well, what's the proof of that? How do you prove that for any two permutations of the input, if one accepts, the other accepts? Like that's what we're trying to do in some sense, right? So that's like assuming the conclusion. Doesn't quite work, right? But actually we're super close, okay? So like that observation already reduces us to a very simple case. We're entirely above the x-axis, let's say, right? So we know this is all going to be zeros, right? Like everything here is going to be zeros, right? In our in Tom's run, right? So all we need to do is say that there is some substring, right, that we can induct on, and then we're done, right? Yeah.
Would you be able to cancel out repeatedly like 0 ones within the string?
Right, good. So, okay, so what he's saying is that a way to build a smaller substring would be to cancel out some pair of 0 and 1, right? Which was actually like the idea that she had in the beginning, which I think I erased. But sorry, yeah, the idea was exactly like canceling out some 0 and a 1, right? And note that we only need to get a string that is even a little bit smaller, right? So all you need to do is show me 1 0 and 1 1 that must exist somewhere in that string that we can cancel out while keeping everything contiguous, and then we can induct, right? So we're really, really, really close, yeah.
But don't we have that on the local maximum or local minimum? Like we add 1 and then we pop 1.
Perfect, yeah. So let's look at the minimum, right? So like right here, we know that the very first thing must have been, in this case, a 0.
Yeah.
And we went up. And we also know, by what she said, that we never hit all the way to the bottom until the very end, right? So there's also some 1 right at the very end, right? Those two cancel each other out, right? That's a perfect example of something which, like we've removed a 0 from the beginning of our string. We've removed a 1 from the end of our string. This internal string x also has an equal number of zeros and ones, right? And now all we need to do is kind of draw this line, right? I draw this line, And like that's my new bottom of the stack, right? So I did push a 0 here, and I did pop the 0 here. But by induction on x, whatever happened here worked, right? We did actually end up with an empty stack from the point of view of this new line, right? So this is going to be an empty stack for the purpose of this like raised machine. And then we remember, oh no, actually there was another 0 on the stack, and we just pop it, and we get it to work, right? So this is it. You don't need to raise your hands. Like, this is the proof, okay? Like, the proof is done now, right? There are only 2 cases in the induction. One is if we ever cross the x-axis, right? Then we have a left and a right case. And the other case is that if we didn't cross the x-axis, then let's just say we were above it. In like equivalently, same proof works if we're below it. And if we're above it, we can just take the first and the last string, the first and the last letter, I should say. We know that it's going to be a 0 and a 1, or symmetrically a 1 and a 0. Whatever is in between has an equal number of 0s and 1s, therefore, right? And whatever the stack was, it'll just be above it, because, this potentially could have come all the way to the bottom here. Like maybe it went like that. That's fine. That's another possibility. But whatever it was, it never crossed below this line, right? Just by induction, like by the fact that we didn't use the other case. And therefore, the machine will accept, right? So this way of doing the induction through these 2 cases is successful and will always work. Questions?
You should acknowledge that you just have to split it again, right? When you do that.
The next time. Yeah. But remember, the way an induction proof works, we only have to do it once. Yeah, exactly. Yeah. If we did this, then the next time around, we would split it into these 2 cases, and we would induct separately on each side, right? So in this way, we're always like inducting on like the mountain range, right? Like if the mountain never goes all the way to the bottom, then we induct it and we split into cases. And remember, the mountain just going straight up, then we just raise the bottom up, right? Yes, question?
So when I initially brought up the induction as part of the proof, what I had in mind was having 2 base cases, 0, 1, and 1, 0 as the 2 substrate.
Yes.
Is it the same,
Yeah.
concept in this case?
Yeah, it is. I can see people are deciding that we're out of time. But yeah, like this was the case of 0, 1. And the symmetric case of 1, 0, we didn't bother to draw. So you're exactly right. OK, but that works. And then we will continue thinking about these machines on Wednesday. Thanks, everyone. Yes?
Can you formalize the induction hypothesis we're inducting on?
Yes. So also, by the way, I should have mentioned, this is in the book.
Oh, okay.
So
Nice,
you can take a look at it in the book.
Okay.
But honestly, though, I would encourage you to try on your own before you look in the book. Like, what do you think that the right induction hypothesis should be?
For all x in O, if x's length is smaller than n, then the machine accepts.
Yeah,
And-
that's it. That's all it is.
Oh, okay.
Yeah.
But I'm confused because now we want to consider a new string, right? X prime. Do we just say that it must be like n plus 2? Or?
Yeah, it must be n plus 2, right? Like you
But
mentioned.
n could be an odd number. It's
But-
vacuously true, right?
Right, but remember, like that's why I made this comment here, right? That because it's trivial to observe that m accepts implies x is in L equals, we only need to consider the converse. So we can anyway just assume that x is in L equals. If x is in L equals, then we already know that implies that the length of x is even.
I was just confused about the n because your n could
Right.
technically be x plus 1, right? The length.
Sure.
of x is-
But as you said, that's trivial because we already know that that doesn't count.
Yeah.
So
Okay.
so the right induction is for n plus 2.
Okay, cool.
Yeah.
Thank you.
Sure.
Question.
Yes.
That last part, should I get it?
Yes.
Did it ask what?
Also, hey,
Yes.
I get a token.
Yes, of course. Yeah.
Quick question on like an alternate way to prove like this thing. I was
Okay.
thinking that can I possibly claim that using this run, the stack is always maintained at the lowest possible size? So it's like
Yeah, that's actually
and
also
then-
equivalent.
And then I can say that if the
Yeah.
string becomes it has to end with 0. It's gonna
Yep.
be at the end.
Yeah. Awesome. Sure.
Like,
Also, wait, someone. Okay. I need to give. Okay, hold on. Someone is recording, right? All right, maybe I'll just.